This training module is an overview of synoptic storm event precipitation statistics that are used to analyze rainfall-runoff events. Synoptic storm event precipitation statistics are calculated by grouping hourly rainfall measurements into a series of events separated by a minimum number of consecutive hours without rainfall. These statistics commonly are used as a framework for monitoring and modeling stormwater runoff quality. This is training module 3.01a for the Stochastic Empirical Loading and Dilution Model SELDM. This presentation has 18 slides and will take about 12 minutes. It was prepared by the U.S. Geological Survey in cooperation with the Federal Highway Administration. This training module has 4 learning objectives. At the end of this module, you should be able to define the synoptic precipitation statistics commonly used for runoff quality analyses, describe the U.S. EPA definition of a runoff generating event, describe rain zones and ecoregions, and discuss regional and local variability in precipitation statistics. This presentation is a brief overview of technical details for estimating and using storm event precipitation statistics for runoff quality analyses. Please see the SELDM Storm Flow Report FHWA-HEP-09-005 and the SELDM Manual USGS Techniques and Methods 4C3 for more details. Appendix 3 of the Federal Highway Storm Flow Report includes a literature review that provides an overview of studies characterizing storm event precipitation statistics. Synoptic storm events are defined by grouping hourly pulses of precipitation that occur within the minimum inter-event time. Precipitation statistics are calculated from hourly precipitation data for use in SELDM. These graphs show the precipitation intensity in inches per hour on the vertical axis and time in hours on the horizontal axis. The schematic diagram is an example showing the process for lumping hourly rainfall pulses into synoptic events. Each bar on the upper timeline, which is labeled A, hourly precipitation data, represents a 1-hour pulse of precipitation. The minimum inter-event time is used to either separate pulses into different storm events or lump pulses within an event. The example of the inter-event time on the left shows 2 periods of precipitation that occur with a separation greater than the inter-event time. Thus, they are segregated into 2 events. The example of the inter-event time on the right shows a series of contiguous 1-hour pulses followed by a dry period and another 1-hour pulse that occurs within the inter-event time. In this case, the final pulse is lumped into the larger event. Each bar in the bottom timeline shows the synoptic storm events corresponding to the cluster of hourly pulses in the upper timeline. Each event has a duration equal to the time between the beginning of the first pulse and the end of the last pulse. Each event has a volume that is equal to the sum of precipitation that occurs during that event. The United States Environmental Protection Agency has defined a synoptic runoff generating storm event as having a minimum volume of 0.1 inch of liquid precipitation and a minimum inter-event time of 6 hours. The minimum event duration of 1 hour is a result of using hourly precipitation data. The minimum interval between storm event midpoints is the result of the 6-hour minimum inter-event time added to the midpoints of 2 1-hour events. This definition has been used by the United States Environmental Protection Agency, the Federal Highway Administration, the U.S. Geological Survey, and other federal and state water resource management agencies. These precipitation event variables commonly are modeled with the 2-parameter exponential distribution because there are many small values and fewer large values. This graph shows a histogram of precipitation data. The vertical axis shows the number of events in each category, and the horizontal axis shows the value of the storm event variable, which may be volume, duration, or the time between storm midpoints. The first bar is missing because the US EPA definition of a runoff producing event has a minimum value for each variable. Thus, the 2-parameter exponential distribution is characterized by the minimum and mean values. The US EPA has defined 15 rain zones within the conterminous United States for planning and analysis purposes. The US EPA calculated the regional statistics for these zones using only 136 sites with data collected during the 1949 through 1987 period. These regions are used to lump areas with similar precipitation characteristics. These regions are the Northeast, Northeast Coastal, Mid-Atlantic, Central, North Central, Southeast, East Gulf, East Texas, West Texas, Southwest, West Inland, Pacific Southwest, Northwest Inland, Pacific Central, and Pacific Northwest regions. Synoptic precipitation statistics between and within regions can vary substantially. The SELDM project developed new statistics from 2,610 hourly precipitation data stations for the 15 rain zones and 84 EPA Level 3 ecoregions. On this map, the precipitation stations are the white dots, the rain zones are the thick black lines, state boundaries are the gray lines, and the ecoregions are the pastel-colored polygons. There are more than 6,000 stations in the National Weather Service database, but the 2,610 selected stations have at least 25 years of record during the 1965 through 2006 period. In SELDM, you can use the average or median value of all stations in a rain zone or ecoregion, or you can select statistics from nearby sites. This graph, made with values from 2,610 precipitation monitoring stations, shows that there may be substantial variability in the average event volume statistics within and among rain zones. The vertical axis is the average storm event volume. The horizontal axis identifies the rain zones. The vertical yellow bars show the range in average storm event volumes within the rain zone. The yellow circle shows the average of stations in the rain zone. Rain zones 11, 12, 14, and 15 have especially large ranges in the average event volume among monitoring stations. In these regions, it may be best to select statistics from one or more nearby monitoring stations. However, it should be noted that even the least variable region, number 2, has a range of about 29% of the average. This graph shows there also may be substantial variability in the average event duration statistics within and among rain zones. The vertical axis is the average storm event duration in hours. The horizontal axis identifies the rain zones. The vertical yellow bars show the range and average storm event durations within the rain zone. The yellow circle shows the average of stations in the rain zone. Rain zones 14 and 15 have especially large ranges in the average event durations among monitoring stations. In these regions, it may be best to select statistics from one or more nearby monitoring stations. However, even the least variable region, number 9, has a range of about 60% of the average value. This graph shows that there also may be substantial variability in the average time between event midpoint statistics within and among rain zones. The vertical axis is the average time between event midpoints, known as delta, in hours. The horizontal axis identifies the rain zone. The vertical yellow bars show the range and average time between event midpoints within the rain zones. The yellow circle shows the average of stations in the rain zone. Rain zones 10, 11, and 13 have especially large ranges in the average time between event midpoints among monitoring stations. In these regions, it may be best to select statistics from one or more nearby monitoring stations. However, it should be noted that even in the least variable regions have ranges of about 50% of the average value. In some cases, using ecoregions or selecting statistics from nearby sites can improve rain zone estimates. For example, rain zone 11 has large ranges for the precipitation volume, duration, and average time between event midpoints. The graphic on the left shows the southwestern portion of the United States, which includes rain zone 11. State borders are gray, rain zone borders are black. Ecoregions are the colored, rasterized polygons. The white numbers are the rain zone numbers. The black numbers indicate the ecoregions that intersect rain zone 11. These ecoregion numbers are 5, 6, 7, 8, 13, 14, 80, and 81. The graphic on the right shows the same area with individual precipitation stations represented as white circles with a black outline. This graph shows that there may be substantial variability in precipitation statistics within a rain zone or ecoregion. The vertical axis is the average storm event volume. The horizontal axis identifies the rain zone, RZ11, and the 8 ecoregions that intersect rain zone 11. The vertical yellow bars show the range and average storm event volumes. The yellow circle shows the average of stations in the rain zone or ecoregion. There are substantial differences between rain zone statistics and the ecoregion statistics because the statistics for the ecoregions are calculated with data from stations outside rain zone 11. Ecoregion statistics may be sufficient for ecoregions 7, 13, 14, and 80 because the variability is relatively small, but statistics from specific sites may be needed for other ecoregions. The contour plot of average storm event precipitation volume in rain zone 11 indicates this zone is fairly homogeneous, with the exception of 2 areas of relatively high precipitation volume. Although most of the area in this region has an average precipitation of about 0.4 inches per event, the statistics from stations in the wetter areas increase the regional average event volume to 0.6 inches per event. The median for all sites in Rain Zone 11 is 0.485 inches per event. The average for the ecoregions 13 and 14 are 0.39 and 0.45 inches respectively. Therefore, some knowledge of the area may be beneficial for selecting ecoregions or nearby sites to obtain your precipitation estimates. This is a map of the annual average precipitation generated using a PRISM analysis. PRISM maps are the parameter elevation regression on independent slopes model. It was developed by Oregon State University for the Natural Resources Conservation Service. These are not synoptic statistics, but such maps can be used to guide your choice in selecting precipitation statistics. These maps are the total annual precipitation, which is greater than the runoff generating event values for SELDM, because PRISM totals include events between 0.01 and 0.1 inches of precipitation. PRISM is an analytical tool that uses point data, a digital elevation model, and other spatial datasets to generate gridded estimates of precipitation statistics. These are the PRISM annual average precipitation maps for the Southwest and the Northeast. We can see the large variation present in the Southwest and the relatively small variation in the Northeast. Regions may not be good for highly variable areas, and the PRISM maps may help identify local similarities and differences. You can go to the PRISM online viewer and zoom in to your site to assess your local conditions. As indicated by these maps, the closest station may not provide the best statistical estimates for your site of interest. The SELDM station selection form indicates that in this area there are large variations in statistics among nearby monitoring stations. The station at Huntington Lake has 33 storms per year and almost 36 inches of precipitation per year on average. The next nearest station, Florence Lake, has only 25 storms and about 18 inches of precipitation per year on average. The Florence Lake values are similar to values at most of the other nearby gauges. In this case, further investigation may be warranted before selecting representative statistics for a site in this area. For example, the elevation of different stations may have an influence on local values. In this training module, we learn to define the synoptic precipitation statistics commonly used for runoff quality analyses, describe the USEPA definition of a runoff generating event, which has a minimum volume of 0.1 inch of liquid precipitation and a minimum inter-event time of 6 hours, describe use of the 15 rain zones and 84 level 3 ecoregions, and discuss regional and local variability in precipitation statistics.